Okay, so I'm going to try to divide my time up sort of evenly to touch on 3 different dimensions of nuclear energy which are important to thinking about its future role. The first is going to be security. The second is going to be waste. And then the third I'll touch on will be the flexibility question. And they all are interrelated in some sense. So let me dive into security. I think there was a really important point made earlier by a number of people, which is that human impacts on the environment, really big ones are energy and agriculture and food. But war and conflict actually can rank up in that same scale if you get them wrong. So on the security side, with nuclear technology, there's more obvious direct linkages. And I'd like to discuss the 2 most important, which are non-proliferation. This involves the proliferation. And then I'm also going to do the physical security part. And it's been a real battle within the nuclear field, first of all, to get people to even want to talk about this being a problem for nuclear energy or something that's important. And then more generally, to differentiate between the behavior of states and the behavior of terrorists and criminals. So let me just point, what is the single most important thing that connects nuclear energy or that mitigates risks for nonproliferation? And that's IAEA safeguards. That's the key thing, and this is actually, we've spent a lot of effort developing an international regime for security that includes the passage of a non-proliferation treaty and broad adoption, and then we have this international institution, an agency of the United Nations called the International Atomic Energy Agency, which is responsible for monitoring and auditing all of the nuclear infrastructure in countries that are party to the NPT. And the effectiveness in doing that is really important for global security. And there's a few illustrations you can look at where we've found the need to improve the effectiveness of safeguards. The first was really 1990, when we went to war with Iraq because they had invaded Kuwait, and then subsequently discovered a clandestine enrichment program the IAEA had been unaware of. This led to changes within the IAEA's monitoring to allow voluntary adoption of additional protocol to monitor for those sorts of activities. Another important example is South Africa, which had a weapons program, and it took the off-ramp of putting all of that into the under IAEA safeguards monitoring and back into the civil energy sector, because when the transition in government occurred, the previous government didn't want to hand nuclear weapons to the incoming government. Another important example is 2003, when we were again going to go back to war with Iraq, and in this case, the US government refused to believe the IAEA assessments that there were no weapons programs in that country. And then the most recent and really important example of trying to use this institution as an off-ramp has been the agreement with the state of Iran that has been negotiated recently, which essentially is an agreement to place their infrastructure under more rigorous safeguards and to cease certain types of activities. Now, doing this really well is something that you need to do anyhow if you're a competent business. Having knowledge and control over where materials are and a robust ability to independently audit that and prove that you know what's going on is something that we need to do really well. And so security actually, in the modern way of looking at it, is very closely linked to how we do safety and how we achieve reliability in these systems. And if you think about these things synergistically, it helps a lot. Next, physical security, 2 main things to think about: theft of materials and sabotage of facilities. The most important issue for sabotage is the fact that when you look at safety of nuclear energy systems, the big issue is the reactors. The rest of it is easy to manage. Reactors operate with really large inventories of short-lived fission products that are extremely toxic, and if you shut them down and don't remove heat, you get rapidly into very serious trouble, right? And you can either have that happen accidentally or we worry about it happening deliberately. The biggest change that makes it much easier to do security for reactors is passive safety, which I've worked on a lot in the last 2 decades, because the AP1000 is the first reactor ever deployed commercially where the method to shut it down and place it into a safe state where decay heat removal occurs requires no external source of electrical power, and you activate it by removing instrument power, by removing control, by removing instrument air, and you don't need active heat sink, and all of that equipment is hardened and very difficult to get access to in an unauthorized way, which is radically different from our existing plants where if I can get in and damage a target set outside of containment that is easily accessible because it's designed so that operators can go surveil it every day, then I can cause fuel damage and a very bad mess. The second is theft, and the key thing we need to do with theft is to eliminate use of HEU and separated plutonium pervasively, right? Because theft of these materials is a really big deal, and providing physical security for them is really expensive because of how intensive it is, and there's absolutely no need to have these materials. Once they're not present in the system, physical security is a lot easier, and that feeds into higher levels of safety and reliability as well. So waste. 3 major elements: interim storage. This is how we do it. Deep geologic disposal. And reprocessing. Let me start with deep geologic disposal. Sally's an expert on this as well. There's a really important point about deep geologic disposal. While it has been challenging to overcome political and societal barriers to getting it deployed, I think that there's a broad scientific consensus that's just as strong as what we have for climate change, that it can be done safely if you pick proper media, and that it's affordable and workable. The next major area of broad consensus is that interim storage of these materials can be done safely and affordably as well. And this means, this is an important message. Waste is not the big problem for nuclear energy in terms of transferring a massive burden to future generations. It's burning fossil fuels and using our atmosphere as the waste dump, because there is no technologically or scientifically credible method. Well, we're talking about the ability to reverse that process. Vastly harder than the burden we're transferring in terms of waste. And if you say that you're going to eliminate waste, you get into doing things with reprocessing, which with the current technology take you back to having that big problem. And there's no need to be doing that either, because future reactors can be different and can use different fuel cycles. Finally, flexibility, and I have 5 minutes? Okay, good. Flexibility. So, nuclear energy systems can be flexible. The ones that we built in the United States were not designed explicitly for that, but the key elements of flexibility come from, first of all, the fact that if you operate them with high reliability, your capacity factor is determined by generally how much time you spend on refueling and maintenance outages, which in the United States today is about 8%, and there's about a 2% forced outage rate within the fleet. And doing that part well, low forced outage rate comes back to doing all of this well. Being really competent here is a good thing. So you schedule those outages during periods of seasonally low demand, just like we do with the fossil units, which are run well, where every time you cycle it up and down, you check a box, and that adds up in terms of okay, we're going to have to take this out and do some maintenance. Okay, so that's one dimension of flexibility. The next is that we know that every single energy technology that we've been talking about, as you scale up its penetration, whether it's storage or demand response or wind or solar or nuclear, the marginal benefit of adding the next increment will be lower because they all eat their own lunch to some degree. And that's true for nuclear as well. So all of these technologies need to have the capability to be curtailed in order to be economically efficient. And with nuclear, the major issues for curtailment involve the ability to ramp power, and that's really determined by thermal stresses in the system. And if we go to smaller reactors, in general, they can ramp faster. And then for thermal spectrum reactors that don't use liquid fuel, we have xenon, which limits the amount you can ramp down, generally to about 50 to 60%. Before, you'll just have to shut the reactor down because of the resulting reactivity transient that you're going to experience. So reactors can be curtailed, and it's done routinely in France, and it just needs to be a necessary an element of the design. Now, there's another dimension to flexibility which merits some discussion, and that is the sort of the evolution that we had with the big incumbent firms making assumptions once they down-selected the water-cooled reactors that required these active safety systems that were expensive and then required high-pressure, low-leakage containments because it was a unique combination of fuel and coolant, the only one where when you damage fuel, you mobilize cesium and iodine in the form of fine aerosol particles, and you have intrinsically high pressure. And so sort of like the space shuttle, the issue that you ran into was that it was expensive to try to get this to work. How were you going to make it cheap? And the solution that was adopted was to make the reactors progressively bigger and bigger and bigger. And this has just not worked out well. So this is one of the reasons why looking at smaller reactors and multi-unit configuration is likely to improve flexibility because construction times can be shorter and you can do more of your manufacturing in a factory setting. And that means that you have shorter time scales. The next area of opportunity is once you've gone past sort of your new scale type of designs, which are smaller light water reactors, where you've retired the risk associated with how you regulate things like control rooms. Under current, I have to quickly finish. Under current NRC regulations, new scale with 12 modules, their control room would have to have 48 operators. Right? They've come up with an approach to put in 6 that's quite logical and is logically quite safe. There's uncertainty as to whether or not they will be approved to do that. The risk that they're taking on can't be recovered. You can't patent that NRC decision. Everybody can free ride on it, and therefore it's logical that we're subsidizing them to do the development to understand how to make the control rooms work. Once they retire that risk, the barriers to doing the first stage of non-water cooled reactors that are small and multi-unit will be reduced as well. And so there's a scaling, and hopefully a part of that scaling is to start shifting towards not expecting components that operate in severe environments to last for 60 years, and instead to go to more frequent replacement. And I'll stop there.
Okay, great.
If you could design the reactors as you think they should be designed and reach the safety goals in the most cost-effective way, how much do you think nuclear power would cost relative to today?
Okay, so let me start at a high level and emphasize that my personal opinion about the best way to design reactors may not be correct. And so as a matter of policy, I really want a framework where multiple approaches are being tried, and I'd really prefer to transfer that framework out of the conventional government development process like France is using, and to launch something. Well, DOE has just this year launched something that looks remarkably similar to NASA's Commercial Orbital Transportation Services program, which was launched a decade ago. And if you go to Wikipedia and look at COTS, you'll find that there is a table that gives a long list of names of different companies that had applied for funding and were also going to be given access to key things like launch range facilities. And there were 2 obscure little startup companies in that list that got funded. One was named SpaceX, one was named Orbital Sciences, right? They were obscure back in the time. I think that we'll run that experiment this coming decade. And it may have the potential to answer this question. If you want to know specifically about what the startup company that is going to be spun out of Berkeley this coming year is going to focus on, it's going to be with molten salt technology, because that's the place I believe has the highest potential for rapid and substantial improvement over what's been done before.
Can I just make one intervention? We just commissioned a survey of 12 advanced reactor developers who tried to assess their cost claims and so forth with some third-party verification. I'll circulate the results. The spread for these Gen 4 non-light water reactors came out somewhere, what we think plausible, we'll try to do it on the ground, somewhere between about installed per kilowatt, $1,500 and about $3,000 on the high side. So, probably 2 or 3 times cheaper than current light water reactors.
It's just like space launch. The space shuttle had a lifetime launch cost of $60,000 per kilogram. And that's because it was just a horribly bad set of decisions about the architecture of the system, in some ways comparable to the EPR, right? And then if you look at what SpaceX charges today, it's $4,600 per kilogram. The steel, concrete, and copper in an AP1000 contributes less than 1% to the $5,000 per kilowatt price that they charge to build it. It contributes 11% to the cost of a Vestas wind turbine at $1,750 per kilowatt. And so the things that make nuclear energy expensive are things which are not fixed by physics. It's something wrong with how we've gone about developing and deploying the technology.
So what is the rest of the cost?
Oh, paperwork and really long construction times. And horribly underutilized manufacturing. There's a lot of, if you look at just the fixtures and stuff required to frame up stuff so that you can weld it together, and you use that once or twice at a plant site, this is just, there's good reasons why really big reactors are expensive to build.
Ken, there's a cost component analysis breakdown in what
And
I'm circulating.
there's really brilliant work that's been done by Third Way Clean Air Task Force also.
Per, would it be oversimplifying to say that the big cost decrement for the non-light water is getting rid of the pressurized environment, the steel and concrete for the vessel? That takes a lot of concrete and steel out of the process. Is that an oversimplification?
It could be. The economies of scale become much friendlier to smaller reactors once you've gone to passive safety. I mean, you can understand why there was this huge pressure with the light water reactors with active safety to try to scale them up in size, because on paper it would make them less expensive. The low pressure designs have much simpler structures that they can go into, but it's very complicated. If you look at how SpaceX got to really cheap rockets, it's really the selection of very good strategy in terms of avoiding liquid hydrogen and going with kerosene. And then the really interesting next step will be liquefied natural gas to replace the kerosene, because it's about the same temperature as the liquid oxygen. And so it's more about making good decisions, and I don't think government-run programs have been very effective at doing it. We really need to run the experiment that is going to be run this coming decade.
Thanks, Joan.
Yeah, I was wondering if you could talk a little more about breeder reactors and closed cycles reprocessing, and what the how you see that playing a role.
Well, when I was a graduate student at Berkeley in mechanical engineering, I took Energy and Resources 100 from John Holdren. So I constantly return to trying to channel John Holdren, because I really admire his way of looking at these things. I think that the key thing about fuel supply is that uranium is cheap. And we know that there's been enough work done that at about 4 times current prices for uranium, you could extract it from seawater, right? So cost of fuel is not logically, in the next few to several decades, going to emerge as a motivation for doing any reprocessing, right? And moreover, reprocessing does not eliminate the need to develop deep geologic disposal. And once you've got it, it's cheap. If you look at the cost of deep geologic disposal of spent fuel, it's really inexpensive. So I've observed some lack of discipline in the environmental and anti-nuclear groups over the last decade of keeping on message that we don't need to reprocess in the near term, because it's just going to make nuclear energy more expensive, and moreover, you're taking on a big burden if you do this, and if you recycle back in light water reactors, you're forced to do that, because the fuel is so hard to fabricate, these oxide pellets, that you have to do it in an environment where you can tinker with the equipment. But it's extreme. This is oxide powders is the most toxic form you can handle plutonium in, and therefore you get sucked into doing something which is really expensive. And whereas you can just store this in interim storage, and when we have our molten salt reactors.
So you would see improvements in extraction as being, well, let's say we're out 20%.
What I think we should do is we should have a fuel cycle which is driven by compliance with security principles and by cost, and it will optimize towards sending waste to geologic disposal because it's cheap and it is safe.
I think I'm next. I think I have 3 points to ask questions about. First, how should we be thinking about the grand range of nuclear costs internationally?
Yeah.
Where's the signal in the noise? Secondly, what about SMRs? I mean, how do we think about those, and how do we even characterize them going forward, because there aren't any good cost estimates and things like that? And what about their flexibility? And then third, kind of per what the conversation was yesterday, and thinking about nuclear renewable hybrids or decarbonized hybrids with other products out the door, what's your thinking on that? Because the approach there was to try to optimize the economics of a very capital intensive asset and find lots of different uses for that. So 3 pieces, if you could.
And of course, you've just asked the most important questions. I think the first one is to add in our existing reactors, which are fully depreciated. They're free, almost, if you want to keep them running. And it is an important question, how long do you run them before you shut them down? Then you get to the question of the construction cost for conventional advanced light water reactors, and they may end up being infinite for the EPRs. We just don't know whether they're going to get any of them actually successfully built. And it really is a problematic design. In the UK, there's very little attention being paid to the fact that there's independent efforts to build AP1000s and ABWRs, and they're looking seriously at SMRs. And AP1000s likely can be deployed at a predictable and not astronomical cost. Because of the degree of modularization that's embedded into the construction, it remains to be proven, but I think of all the technologies, that's the one where you could envision rapid scale up. So I think our experience is that in countries that have had rapid, large deployment, at least in the early phases, costs have been affordable, right, of those deployments. And it's sort of when you're realizing there's no more customers and you need to maintain this manufacturing and other infrastructure that these programs have gotten into trouble. But they have achieved the most rapid rates of decarbonization nuclear has in these previous deployment programs in Sweden and France of anything that's been done, including Germany and Denmark in the last decade. The SMRs, you've got this issue of this competition between the economies of scale versus the economies of mass manufacture. And the one thing that I think we'll find with the SMRs is that they will just have more predictable cost, both in terms of how long it takes to get them deployed and operational, and also in terms of what you're going to get charged for them. We don't know where those costs are going to end up yet, but they could readily be directly competitive with costs of advanced light water reactors, but give you faster deployment cycle. And this gets to the point that what we really need to do is to reduce the time of the life cycle for replacement of these technologies and try to move towards designs where, in fact, components that operate under fairly severe high temperature conditions, you intend to design for replacement. And when in 10 years, when you put in the new whatever, that it actually could be better. And that puts you in the space of being able to give a reasonable warranty. If you look at the warranty that Westinghouse or General Electric or Areva will give you when you buy a large light water reactor from them, it's lousy in terms of the amount of risk that's transferred to the customer that the customer really is not in control of. And I think that the ability to offer better warranties improves a lot as you get to smaller reactors. And you can put risk where it belongs, the way Tesla's been doing. Now, Tesla is a really good example of something that's substantially different, that's being ramped up in deployment, where they've managed the warranty and recall question pretty well.
So two questions. One, the U.S. Navy's been managing, for better or for worse, and I don't know the cost, small nuclear reactors for a long time. Is there a way to leverage that knowledge and expertise towards civilian society and our desire for this? And two, whatever happened to the thorium reactor?
Okay, good. All right. Okay, so the first answer is that the naval reactors are really expensive. And that's why they go in submarines and aircraft carriers, and that's why they haven't put them into other surface ships, right? So they're way too expensive to compete in civilian market. They're also designed. Our naval reactors run with highly enriched uranium, and it would be completely the wrong thing to do to do that in the civilian sphere. I think there's another point of illustration, which is that when the idea of SMRs was first developed by NuScale, a startup spun out of a university, the big incumbents, in this case, reacted by immediately dusting off their old SMR designs. And the incumbent that was sort of crushed NuScale initially, and NuScale was able to crawl back out from after being crushed, but that was B&W, which is the company that makes naval reactors, right? And I think that companies that execute large-scale government projects, particularly procurement for the military, are the last place you really want to go to get good decisions made. We suffer with the Bay Area Rapid Transit System, right, which was developed by Rockwell, and it's taken decades to get it to work at levels which are still mediocre compared to the European technology. So I guess my brief, actually I'm spending more time on the question than I should, but I would not go to the naval reactor people to get substantively better technology, even though they've done a very good job with their particular application.
We have 4 tenants, that's all we're going to do, and let's keep it crisp if we can, Jack.
Okay.
Okay, so you didn't answer thorium, but you also didn't answer the hybrid, because that was my question too. What other co-products and how can these things work, especially with your molten salt idea, which I don't quite understand yet, so you maybe have to explain it.
Okay, so
Co-products.
Very quickly, thorium falls into the same category with the breeder reactors. There's enormous potential with that technology, but uranium is too cheap now to really make it logical to try to get to high conversion ratio of 1 with thorium. With hybrids and with using process heat, that's actually just a much longer discussion. To encapsulate one of the features of the molten salt reactors is that sodium, the other high temperature, low pressure coolant that's been done extensively is sodium, and there's lead. Sodium boils at about a little bit under 800 degrees centigrade, and there's a number of factors that essentially force you to keep your temperatures below 550 with sodium. With the molten salts, they freeze at around 450, and your structural materials lose strength at about 800 to 900. The sweet spot with molten salts where you're going to find them designed is about 600 to 700 degrees. And there's a lot of things you can do with 600 to 700 degrees if you're creative. So that would be the brief answer.
If we just assume that the assumptions that you've put up here could be achieved, all of that can be done, What's the realistic timescale for this next generation of nuclear to actually play a significant role in the power system of the country and the world?
That's, if you look at the analogy with what NASA did, then 10 years from now, you're in a position to initiate large-scale deployment because you've replicated what SpaceX did, or not. If we stay on the same path of large advanced light water reactors and government development programs, then the short answer is no. And there's counterfactuals with SpaceX. The fourth Falcon 1 launch, if it had failed, SpaceX would have gone bankrupt, and today everybody would know that the commercial orbital transport services was a failed model, and the only place to get rockets is to go to Boeing or Lockheed.
Well, it does seem like it's worth then laying out the timeline and what would have to be true to get there, because my concern is that it might be very promising, and these are some pretty challenging things here nonetheless, like especially the first one around nonproliferation, but we have to be very clear about hitting those hurdles. Otherwise, it could be 2050, and we're getting the first of this generations out. And
You're precisely correct, and I don't think it's pragmatic for people who do energy systems policy to presume that there's going to be dramatic success, although it's also, you shouldn't exclude that. I think that the key point is that when you move the decision-making into a startup framework where you've got a burn rate and you really have to make milestones, and you have the capability to bring in people from the conventional industry where they know they'll never accomplish anything significant in their entire career, and get a chance to work on something where they've got a chance of changing the world for the better, that may be the environment where you've got a better chance of actually doing what you need to do, which is to hit those kinds of milestones.
Yeah, so a couple of comments and also questions. First on the comments, I know we want to emphasize the technology, but in the nuclear space and CCS, it's really one of those instances where public perceptions and siting are going to be really the critical issues, either now or for the last 20%, I would say, more than the technology alone. So we've looked at the costs of SMRs, light water SMRs, in a context very similar to this workshop, not in the last 20%, but assuming that we're producing the N-of-a-kind unit. So all the hurdles between now and then would be already solved. And our experts were fairly optimistic. We found a large uncertainty, but that overall you could get the light water SMRs, even the smaller units, like 45 megawatts, to 12 cents per kilowatt hour. So that was the number. Wide range there. Not sure I believe those numbers, but this would be really far out. That would be the source of potential costs. We also found that the construction times wouldn't be an issue. So on average, they would say 5 years. From the first, so again, fairly optimistic, but that's what we found. I think the really interesting issue that Doug was mentioning is what it will take and how many years to get to that point of factory fabrication for if that's the pathway that is followed for SMRs. So really how, and this would be a neat project really is, how many years do you need and what is the sort of learning rate that you'll have to get to that N-of-a-kind sort of project. So those are more comments, but now the question is, one of the things that folks at CMU are studying is the potential for floating SMRs, potentially, which is far out, but we're looking at the last 20%, and potentially to address issues of seasonality, for example, gaps and so on. There's tremendous regulatory issues and even technical issues on that front. So would you comment on whether you think this is something?
Because actually Armin and I have a paper coming out on cooperation with China, with Jim Hansen, Richard Lester, Junji Chao, and Hongji Zhu, U.S.-China cooperation, where, and it'll be tomorrow in Science, but but we highlight the potential of the floating plants, the types of things that MIT has been studying, not tiny ones, but sort of a Westinghouse AP1000 placed into the kind of floating platform where China fabricates the 80% of these large cylindrical ones that have been developed for the North Sea, anchored 10 miles offshore, using all the available technology for offshore wind to transmit power back and forth. And when you start to look at it, the shipyard construction costs to convert steel into something are a factor of several lower than the construction costs to do site construction on land. Yeah. And your time for construction can be a factor of 2 to 3 lower. It's a really important thing to explore.
And just really quickly, why the large scale AP1000 versus 200 megawatts?
Because it fits very nice. First of all, the passive safety, you don't have a bunch of extraneous equipment that you have to add in. It fits nicely into that, the kinds of platforms that are already built, and it's a well understood and known technology. And if you haul these things from the shipyard and anchor them, then it's maybe the fastest path to cutting the construction cost of that kind of plant. There's no site infrastructure to speak of by a factor of a few from what it is today to build in China.
So you think we'll see that in the first 80% perhaps?
Well, it all depends on whether the U.S. and China want to cooperate, and that depends on who wins the presidential election,
It's actually something you might do in the next decade as opposed to the decade following. That was the rationale.
I read about all the benefit of the smaller reactor, and they are cheaper and quicker to build. But the first one, the HER200 in China, seems to be taking a very long time. And according to what I read in the news, the next one they want to build is HER1000. They want to go big. With all the advantage of being small. They want
the high temperature gas?
Yeah.
Okay. I think helium may be a dead-end coolant in the sense that what you end up with the modular designs are really big and bulky. So if you just do material quantities that are embedded into the helium-cooled reactors, they're enormous. And that's one of the reasons why we're working on pebble fuel. We're cooperating with the Shanghai Institute of Applied Physics because they're going to source pebble fuel for a test reactor from the HTR program. But as soon as you cool it with a liquid, and the fluoride salts are quite nicely compatible with graphite and with high nickel alloy structural materials, everything becomes vastly more compact. And so it's a very interesting direction to go in high temperature reactors from helium to salts because you go low pressure and far more compact, far higher power density. But the HTR PMs, I think they'll have a limited market segments just because they're really big and bulky machines.
All right, thank you very much.